Welcome to 1.3 Notes, where we are talking about continuity and end behavior. In order to describe that, we're actually going to use limits. So let's jump into continuity. So when we first talk about a function, or even just a graph in general, it doesn't necessarily have to be a function, we usually are used to working with continuous graphs, or something that does not have a break, hole, or gap. So, does not have any breaks, holes, or gaps. And then, of course, if a function or if a graph does have breaks, holes, or gap, that's what we call discontinuous. Simply just meaning that, hey, it's not, that's what the definition of it is it's not a continuous graph. So when we're talking about discontinuity, we can see it a lot of times in three different ways, at least from PreCalc. You might even get to a few different ways later on. So the ones that we kind of were used to working with are something like this rational function, where as you get closer to zero here, it goes negative, negative, negative infinity. It can't be zero, but then after this way, it jumps up to this positive infinity and comes back down. So when you have these kind of infinite converging here, right, negative infinity and positive infinity, this is infinite discontinuity. Right, it has these two kind of approaching negative infinity and positive infinity. Or it actually could be approaching both positive infinity and then come on over to the other side, right? And then if it actually is approaching a number, and this is kind of one of these piecewise functions that we looked at in terms of the function the other day, but we didn't actually look at it in terms of a graph. So when we have these two kinds of functions and all of a sudden it's approaching here, it comes all the way down here, and then it jumps all the way up and goes over, pretty simple, we call this jump discontinuity. Right, because when we're coming at it from this direction, it's going down here, but when we're coming at it from this direction, it's approaching this number. And this is kind of that preview to what limits would be. And then the last one that we talk about is a hole. And when we talk about holes, we have a few different options. This is called removable discontinuity. And sometimes you just have the hole, right? Sometimes you have this function and there's no value for this. Often, or other times, there might actually be, at this point, x might equal something else. So you might have something down here where x is defined at, for example, here this looks like 1, but if x was defined at 1, it just might not be on the graph that we're used to seeing here. So in terms of discontinuity, we have infinite, jump, and removable. So, and right now you're just kind of looking at the graphs and seeing what those look like. But in terms of end behavior, and that's what's going on at the ends of the functions, and we're used to describing end behavior. So we're used to looking at a graph. Let's try one out here. Just kind of going up there, right? So if we were looking at a graph, we can describe end behavior. We also know that end behavior is classified by your leading coefficient and degree. So just as a reminder on that, that's what classifies that end behavior. That we know that, hey, as x is getting more and more towards infinity, it's also going towards positive infinity. And as x is going more negative and negative infinity, this one's going also positive infinity. Okay, so that's what we did in Algebra 2. We're going to jump on over to a little bit of limits. And for PreCalc, you're just going to be using limit notation. And limits are the concept of approaching a value. but never actually getting there. Right? But never reaching it. So we're not actually getting to that value. So if I have my example here, I have f of x is equal to 1/2 x plus 1, and I want to look at this limit as x equals 1. So I know that, hey, at x equals 1, we're going to be equal to 3/2, right? So that's the value, that's the output. Input is 1, output is 3/2. But what I want to do is I want to say, hey, when we are coming at it from this side, what's going on? And as we're coming at it from the other side, what's going on? Like, how close are we getting to this? So when we're writing limits, all right, this is a little bit of some new notation. Usually what you see is you see a cursive L, sometimes not, it's just an L, and you say lim, right? So the L-I-M, and we're talking about the limit. And we're talking about the limit of f of x. So we want to make sure that we know what function we're talking about. So Lim of f of x, excuse me. And then we're going to go ahead and I'm going to say as x approaches, so I'm putting this little x below it, and as x approaches 1. Now, sometimes we're going to see this in a few different ways. I'm actually going to start, well, actually we'll start here. So as x approaches 1, and we know that's going to be equal to 3/2 or 1.5, right? So as x approaches 1 here, we're going to go ahead, we're getting closer and closer to this 3/2. It's equal to that. Now, you might see a little bit of this too, which is that you might have the limit of f of x as x approaches 1, and then I'm going to put a little negative sign on the right. And what that's talking about is, hey, as it's approaching from the negative side, okay? So from the left here, what's it getting closer to? And that's going to be equal to 3/2 here, obviously. And again, we want to describe the limit of f of x as x approaches 1 from the right side. So from the right side, I'm going to put a positive, right? So we're talking about it from this one. And again, that's going to be equal to 3/2. And why these little plus and minus signs are important is because I'm going to scroll back up here to our types of discontinuity. And if I'm thinking about this one, hey, let's call this -1. So as we're coming at this from the left, we have an output here. We're getting closer to this value. But as we approach it from the right, it's a different value. And that's what makes a lot of this jump discontinuity. So when we're using our in behavior, or if we're even talking about the in behavior of this function, right? This is going to be going towards positive infinity. This one's going to be going towards negative infinity. So let's go back over here to our example 1, and let's talk about our in behavior using limit notation. So we're going to have the limit, and let's go ahead and let's just call this g of x. The limit of g of x as x approaches infinity is equal to, so we're saying, hey, as x goes more and more this way, it's going to go towards infinity, right? We used to say, hey, as x approaches infinity, g of x approaches infinity. Now it's this kind of new notation. And again, I also want to describe the other way. So the limit of g of x as x approaches negative infinity is equal to infinity as well. So when we're thinking about in behavior now, we're now going to use this limit notation here, right? Limit notation. So let's try one more example. This one, I'm just going to go ahead and I'm going to give you a function. Let's say h of x is equal to, let's see, negative 3x to the 5th plus 2x. All right, so if you kind of think about this function, it has a negative leading coefficient, but a odd degree. So you can be doing a little dance with your hands. And I'm describing in behavior. You either could kind of sketch this and kind of figure it out, or I'm going to say, hey, the limit of h of x as x approaches infinity is equal to negative infinity, right? This guy's going down. And then the limit of h of x as x approaches negative infinity is equal to positive infinity. Still the same concepts that we're using, it's just a new way of writing it. So our little note down here is that we are now going to always use limit notation to describe end behavior. So we're always looking for that limit notation now. And on the AP test, you are going to see limit notation. So you need to be able to kind of understand or maybe match up a graph with these types of limits. All right, so let's go ahead and let's kind of dive into a hefty example here, which is we're looking for, is the function continuous? If not, we're going to explain the discontinuity, and then we're also going to describe the end behavior in limit notation. So that limit notation is pretty important. All right, let's go ahead and use the function f of x. So we're going to say f of x is equal to x plus 3 is on the numerator over x squared plus x minus 6. I want to get this into something that maybe I can see a little bit easier. So I'm going to go ahead and I am going to factor our denominator. So we have x plus 3 over x plus 3, x minus 2. And I see that the x plus 3 cancels out. So a simplified form might look like, I'm not quite a fan of writing over horizontally, but ran out of room a little bit. X minus 2, and what we would say, of course, is a whole at x is equal to negative 3, right? And now, we might not use the term whole. We would probably use the term, hey, we have jump discontinuity. At x equals negative 3. And you can simply just say that, right? They probably on the AP test are looking for that. But let's talk about it in terms of limits and get used to our limit notation on this one. It's probably easier if we graph this. So I am looking at my rational function here. I have x minus 2, meaning that I have a horizontal transformation. I'm actually going to start with my asymptote here. And I know that I don't have any vertical transformations, so I'm going to draw an asymptote there. I don't have a stretch, so I'm going here for 1. But I do know that I have a hole at negative 3, so I'm going to go over negative to negative 3 and remind myself that I have a hole there, and then I'm going to graph my function. Just a bit of a sketch so that I can see it. Not my best sketch in the world, but again, this is just so that we can kind of see what this is looking like and what kind of discontinuity that we have here. So we know we have jump discontinuity at x equals negative 3. So I'm talking about this right here. And the reason that I know it's just jump discontinuity is that, number one, is that as I have the limit of f of x as x approaches negative 3 from the left. I'm going to start from the left. I'm going to come from here, and I'm going to get really, really close to, I'm actually going to plug in negative 3 to this function. So I have negative 3 minus 2, that's negative 5, meaning that we're going to get really, really close to negative 1/5. Okay, so I know that part, but then I'm also going to look at, hey, as the limit of f of x as x approaches negative 3 from the right-hand side, so coming really, really close to this one, again, we're still approaching the same number, so is equal to negative 1/5. Going back to algebra 2, There were some Delta math questions where you would say, hey, there is a hole at the point. I don't want you to write this down, put a different color so you don't write it down. There's a hole at -3, -1/5, right? That would be the hole that we're working with. We're kind of working with a different vocabulary here. So we know that these two things are equal to the same number. So they're equal to the same number, but we know that f of -3 is undefined, right? If we plugged in -3 to our function, if we plugged in -3 here and we tried to plug it into this, we would not be able to get an output. It would be undefined. So what we can say is, hey, the left-hand limit and the right-hand limit equal each other, but -3 is undefined. That is the definition of jump discontinuity. Kind of bringing it back to pre-calc only, you need to be able to kind of look at this graph and say, hey, there's a hole. Hole means jump discontinuity, okay? So kind of make it a little bit simple for yourself. Let's look at the other discontinuity that maybe you saw here, is that we also have infinite discontinuity. And we have this infinite discontinuity at our asymptote, our vertical asymptote right here, meaning that we're saying, hey, the limit of f of x as x approaches 2 from the left is equal to -infinity. And the limit, the limit of f of x as x approaches 2 from the right-hand side, right? So we're going really, 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 really close to this way. We're now getting to positive infinity. These things, of course, don't equal each other. And if we want to take it a step further, we also know that f of 2 is undefined, right? F of 2 is undefined. Last part for end behavior. Last part here for our end behavior. A lot of this is so helpful if you just kind of know what your graphs look like and you know what's going on. So this one gets a little bit tricky because we are, of course, our end behavior is going this way and this way, meaning it's getting really, really close to our asymptote. So it's getting really, really close to 0. So we're going to say, hey, the limit of f of x as x approaches positive infinity is getting close to 0. It's okay to have a number. We're talking about how it's behaving at the end of the graph. And your other side, as x approaches -infinity, is equal to 0, right? Same thing there. All right, so definitely a hefty question there. Looking through a lot of limit notation, a lot of it is the same information that we've gotten, just a new type of vocabulary in terms of working with it. Okay, before we move on, I want to kind of jump back to 1.1 with a little bit of an extra practice problem in talking about our domains. So let's define a function of g of x, and it's going to be the square root of x squared plus 2x minus 24. And I'm looking for the domain in interval notation. Interval notation. Here we go. So it's a square root function, and what we of course talked about in terms of a square root function is that everything inside the square root, so this part right here is going to have to be, right, greater than or equal to 0. It's going to have to be a positive number. So I'm going to go ahead and set that up. We have x squared plus 2x minus 24 is greater than or equal to 0. And I'm going to factor it because it's a quadratic, and that's kind of, we had zero product property. What you want to do with a quadratic, it's nice and easy in factored form. So x plus 6, x minus 4, greater than or equal to 0. Now, there's two options because you're multiplying two things together. And we know that they either have to be two positive numbers are going to be greater than or equal to 0, or the other option is that if you actually had two negative numbers multiplied together, that's also going to give you a positive output. So when you have these two different options, definitely important to look at both options. Let's start with the positive one. So let's say, hey, x plus 6 has to be greater than or equal to 0, and x minus 4 has to be greater than or equal to 0. So x has to be greater than or equal to negative 6, and x has to be greater than or equal to 4. Let's think about this kind of just normally, right? Thinking about it as terms of, I got numbers that are greater than or equal to negative 6 and also greater than 4. Well, if a number is greater than 4, it's automatically going to be greater than negative 6. So I'm going to go ahead and I'm going to highlight this. I know I want these numbers that are going to be greater than or equal to 4. Let's actually put that in yellow so you can see it. The pink kind of covered it up. There we go. So we're going to keep those numbers greater than 4. I know that it was going to fit into both categories. Okay, we have to go back again because we have to look at these negative options. So we're going to say x plus 6 has to be less than or equal to 0, and x minus 4 has to be less than or equal to 0. So x has to be less than or equal to negative 6, and x has to be less than or equal to 4. And again, looking at this kind of rationally or just kind of in general, hey, if I have a number that's greater than, less than negative 6, it's also going to be less than 4. But I have a number less than 4, not necessarily here. So I just really care about these numbers right here. I'm going to go back, take that highlighter. I care about this. So in terms of my domain, I want numbers that are either going to be less than negative 6, or I want numbers that are greater than 4. Because the less than negative 6 numbers are going to give me negatives and negatives to give me that positive output. The numbers greater than 4 are going to give me positives, give me that positive output. So if we're thinking about this in terms of our interval notation, hey, I'm going from negative infinity up to negative 6, and I can include negative 6, union 4, infinity. And there's our domain restriction for g of x.